convolutional neural networks that you could learn about in that second week. They are particularly widely used or renowned for their use in machine vision.
I just like to think about really exciting topics, and I always didn't feel comfortable doing the same thing for a long period of time. I feel like I will learn much more by exposing myself to many different disciplines. I think ultimately I'm really interested in intelligence, and to really understand intelligence, I believe we need to look at biology, at people.
Konrad, welcome to the Super Data Science Podcast. It's an absolute honor to have you here. Where are you calling from today?
So I'm at home in Philadelphia. It's a wonderful day with sunshine on the outside, and I haven't left my home in a long time.
Well, I think we're nearing the beginning of the end of the pandemic. So we're recording end of April. And something that's been super exciting for me to watch over the last couple of weeks on Manhattan. So we have, regional specific COVID stats. And 3 weeks ago, we were at a 3% positive test rate. And now we're at a 1% positive test rate with the level of vaccination that's happened here. So you might get to go outside someday soon.
Well, I'm kind of jealous because our numbers, I believe, are factor 3 worse than yours right at this time.
Oh, no.
So hopefully soon.
All right. I hope so as well. Looking forward to a return to normality. So you have an incredible academic background. I'd love for you to tell us in your own words a little bit about what your specializations are. So I know that you have a big specialization in the relationship between biological neural networks and artificial neural networks, like deep learning neural networks. You want to tell us a bit about that?
Yeah, I think ultimately I'm really interested in intelligence. And to really understand intelligence, I believe we need to look at biology, at people. And hence a lot of my research was about how do people solve problems? And I think we also need to look towards neuroscience, where we've been looking, well, what's happening in the brain while we perceive things, while we move? And then lastly, I think we really need to start building artificial intelligence and trying to solve the same kinds of problems that biology is good at solving. So in that sense, I'm interested in all these different aspects of that. And that's why if you actually look at my CV, I look like I'm very badly specialized. I have written papers in lots of different areas. Not like how do we get electrodes into brains? How can we treat various diseases? And how does the brain work? But they all just aim at more or less doing the same thing, which is just understand intelligence broadly construed.
All right, so many exciting things to talk about related to your academic research. I can't wait to dig into it with you. However, first, I would like to talk about the Neuromatch Academy, which is a program that you conceived of that is related to the intersection of your biological and your artificial neural network worlds that you straddle. So this program launched last year for the first time. It's an intensive 3-week summer school on neuroscience, and then separately 3 weeks on deep learning. I assume people can sign up for one or the other or both, depending on their interests. And you're running it again for a second time this summer. So tell us a bit about the program.
That's right. So everything started last year when the pandemic hit. At that point of time, before last year, I was organizing the summer school in neuroscience. How does that work? You bring in 20 or 40 students from worldwide. You bring in 10 lecturers, The lecturers all come, they fly in, they talk for a day, and then they fly back. The students learn a lot in that period of time. And then, of course, when the pandemic hit, that was over. Mm-hmm. And so then we decided, well, what if we could bring this online? In fact, lots of other people had summer schools as well. There's about 10 summer schools in neuroscience. So we all joined forces. So we decided as a big team, we ended up being about 300 people.
Wow.
To try and make a 3-week summer school as the best that we could possibly build as this joint team. Now, how do you do that? Normally a professor brings some tutorial, and the tutorial, is not always so great. If we're in a big team, we can really try and optimize all aspects about that, which is what we did. And we tried to optimize the format. So instead of the usual professor gives lectures and then there's homework work, we went to this format where it's like you just, as a professor, describe 5 minutes what that concept is, and they immediately do it.
Mm.
And we have this format where everything happens in Google Colab. So you see the video explaining things in Colab, and then right below it, you do the exercises. And then comes the next concept. So you learn by doing, and we found that that's incredibly effective in computational neuroscience.
And there's also a tutorial component, like a small class size component. So that's actually where the match in Neuromatch comes from, right?
That's right. We bring people, we believe in the power of groups. So we bring people in small groups, 10 people at a time, with a TA that we pay. And we make it so that these groups are good fits to one another. We run algorithms that match people, bring together groups that have similar interests. What does that mean? We bring together people that speak the same language. And there's a lot of people who prefer that there's someone who they can speak with in another language.
Oh, interesting.
So, for example, we had German, Italian, Mandarin. We had 13 different languages. We also bring people together that are interested in similar things. We bring together people that are at similar stages of their career.
Mm-hmm.
And with that, we can have these groups of learners that really help one another.
So, what kinds of questions do people answer? Do people answer open-ended questions, or do you have specific, like multiple choice questions that people answer about themselves? Do you have an algorithm that matches people, or does it happen all by hand?
Well, if you have thousands of people, matching people by hand is maybe not such a great idea. Full disclosure, we had the idea and we decided that we didn't have the manpower to match people like that.
Mm-hmm.
So, yes, we run algorithms for that. In fact, the whole Neuromatch movement came from before the pandemic hit. We were bringing people together in these mind matching sessions where we introduced pairs of people that we felt had scientific common interests. And they had a great time talking with one another. And before the pandemic hit, we already wanted to bring that online. So once the pandemic hit, we were like basically ready to go. And that's how the movement got off the ground so fast.
So when that was running in person, matching people together like that, even just the one-on-one matching, so that was, I assume, mostly academics. Was that happening physically at the University of Pennsylvania in Philadelphia?
No, it was happening at conferences. So this is absolutely crazy. So you fill a room with like 200 people. They all have little printed cards where it says whom they should meet at which point of time. Someone's in front of everyone and says, "Ding! It's time for session number 3." And then everyone has which table and which person at which table. Now, the main complaint that we get is like, I had great discussions with the people, but it was hard to understand anything because you have a room of like 200 people where every pair of people talks with one another.
Right.
So in that sense, online is much better because we can bring these groups together and also pairs together.
I think it's a good idea. In fact, the Data Science Go virtual conference that Super Data Science organizes, it has a similar kind of thing where you get paired online with somebody. It's kind of like a speed dating experience in that case that you can facilitate online where I haven't actually gone through it myself. So hopefully I'm getting this exactly correct, but it's something like you spend 5 minutes with somebody, although I think that it's random. So maybe there's a real opportunity here to be using some information to be having it be non-random.
Yeah, and our algorithms are all on GitHub, so you're very welcome to try how well that works.
Oh, wow.
And what we do is it's actually quite simple. Now, like everyone describes their interest as a 100-word little abstract. It could be an essay or something. And then just we do simple topic modeling and match people that are similar in this topic space. And then there's a linear programming component to make the groups. Like you need to make sure that every person sees the same number of people. There's a couple of constraints like this.
Very cool. So tell us a bit about the curriculum for the deep learning school. So we'll talk a little bit about the neuroscience school as well, but I think for our audience, probably the deep learning school is probably most interesting. I think it's 3 weeks, right? And so what's the, how much time do people spend every day? And, how does the day break up? I guess you spend part of your day watching those 5-minute lectures and then doing the hands-on code. And then, so then how often do you end up talking with your teammates?
Yeah, that's right. Let's go how the day works. So in the morning, everyone meets in this group of 10 people and they jointly do the tutorials. which is really great because in many components of the tutorial, the students can share a screen. Basically, they'll be in a Zoom breakout room, and the TA can then go from person to person, like look over their shoulder, over their metaphorical shoulder, and help them. And they can then ask, look, I'm having this error, or like, why does my code not do what I think it should be doing? So we find that it's incredibly helpful to have this TA that goes through them. And then, of course, we also have these discussion sections in that group of 10 people where it's like, why do you think FaceNet is a prom from a racism perspective, maybe? So
Right.
there are all those components where people need to talk with one another. And so this happens during the first 4 hours. Like you always do 45 minutes, which are 3 times the 5-minute lectures plus 10 minutes doing it. And then you have 15 minutes break. So that's what happens in the morning. Then you'll have a break. And then in the afternoon, you do projects where you really get together with people with similar interests and start building code in deep learning that you actually use for a project.
So with thousands of students, does morning mean like morning Eastern time in the US, or do you have start times all over the globe?
Well, we are running on 11 time zones. We are running
Wow.
all over the world. Our map of who's taking our course is online, but yes, we have a large group of people from China participating, a large group of people from India
Cool.
participating. We have the Japanese participating.
Wow.
So we are running on 11 time zones. And that means that most of our material is basically localized only within that group of 10 people that are together. And then, of course, we need to have question and answer sessions and mentorship events. And for those, we make sure that we stagger them through the different time zones so that everyone has access. So we are using 3 time zones for that. And then, of course, it means that the local group will at times have to move a little bit to make space for the question and answer session on their respective time zone.
That is
And
so
you can't
cool.
yeah, you can't do global unless you're really on all time zones. There's no
Yeah.
choice.
I've done a lot of conferences online since the pandemic hit, and I have not participated in one that has varying start times like this. That is a really cool approach. I like that. So, what kind of person is ideally suited to taking this? What kind of mathematical or programming background do you already need to have to make use of the deep learning summer school at Neuromatch?
This is a fantastic question. So, for the course to be useful, you need to be able to code in Python because everything is about building neural networks in PyTorch. So, if you don't have Python, this is not a good way of learning Python. So you need Python, and then you need like the basics of what would be part of a data science course. Now, like you need to understand matrices because tensors don't make much sense until you understand matrices. You need to understand basic calculus, like calculate derivatives, the chain rule. You should know some basics about data science, like the need for regularization, L1, L2 regularization, the kinds of things that any data science course will teach you. But how do we define ourselves? We want to be like the gentle course, the course that makes it easy for you to get the skills that you actually need for your career. So therefore, we're trying to do all the things that make it easy to like stick with the program. Now, like you're in a group of 10 people, which means that if you fall out, there's 9 other people who will have gotten to know you during the first days who might send you an email like, hey, John, we are missing you. Why you're not here?
Right.
And the effect of that is that we have very, very little dropout. And the other thing is we have this big group working on the materials. So the materials are just awesome. They're just at the right level. And therefore, what we want to be is this inclusive, positive, friendly space in which you can learn the skills that you really want to have.
You actually, on a previous call that you and I had, you mentioned to me the dropout rates that are normal in these kinds of massive courses. Do you remember that stat?
Yeah, if I remember it right, typical completion rates for MOOCs are
Right.
between 5 and 15%. And in our case, I believe it's 86% of people
Wow.
really make it all the way through the course. And that isn't because we make it easy, it's because we support people at learning the things that they really want to learn.
Brilliant. This episode is brought to you by Super Data Science. Yes, our online membership platform for transitioning into data science and the namesake of the podcast itself. In the Super Data Science platform, we recently launched our new 99-day data scientist study plan, a cheat sheet with week-by-week instructions to get you started as a data scientist in as few as 15 weeks. Each week, you complete tasks in 4 categories. The first is Super Data Science courses to become familiar with the technical foundations of data science. The second is hands-on projects to fill up your portfolio and showcase your knowledge in your job applications. The third is a career toolkit with actions to help you stand out in your job hunting. And the fourth is additional curated resources such as articles, books, and podcasts to expand your learning and stay up to date. To devise this curriculum, we sat down with some of the best data scientists as well as many of our most successful students and came up with the ideal 99-day data scientist study plan to teach you everything you need to succeed, so you can skip the planning and simply focus on learning. We believe the program can be completed in 99 days, and we challenge you to do it. Are you ready? Go to superdatascience.com/challenge, download the 99-day study plan, and use it with your Super Data Science subscription to get started as a data scientist in under 100 days. And now, let's get back to this amazing episode. So in order to take this, you would really need to set aside the time. You need to set aside 3 continuous weeks to study it full time, right?
That's right. Now, like, it runs from August 2nd to August 20th. Every morning you learn, every afternoon you work on your projects. There's not gonna be all that much extra time. Sure, there's if you have a family, you will be able to look after your family at the same time.
Right.
But it's not something where you could realistically do a full 8-hour job and on top of it do like 8 hours of learning. It's time that you need to put aside for this learning task.
Yeah, that makes a lot of sense, especially with the interactivity. I suppose, in that small percent of people who don't make it through on time, I suppose some of them could be going through the materials asynchronously, which of course is something that anyone could do. You can go back and review things.
Yeah, all our materials are open source. All the videos are there. And we had in the neuroscience course, we had a lot of people, they call it slow pod. They basically get together with a posse of friends and just say, we do 1 day of the summer school every week. And then they meet once a week, maybe on a Saturday, and then they go through the materials in detail. And that helps them a great deal. I would like to briefly, if that's fine, John, talk about the curriculum, because I think that's also very important.
Absolutely. It was on my list to ask you. Yeah.
So the idea is that we want to give people the full skill set of deep learning, not at the level where you could mostly be a researcher in that area, but at the level where you can use the things as a data scientist. So it's this project, it's this set of lectures that really build on one another. Like, we will first teach PyTorch, then we will teach about optimization in linear systems, and then we will teach about nonlinear systems, multi-layer perceptrons, and then we will teach about optimization, and we'll teach about regularization. So that way, the first week kind of gives you the basics, the stuff that goes into every neural network you'll ever build. And then we have a second week that uses the tricks that we use to make things working. Like, we'll talk about convnets, we'll talk about recurrent neural networks. We will talk about these more advanced concepts. And then in the third week, we can
explain those a little bit more to the audience in case they don't know as well. So convolutional neural networks that you could learn about in that second week, they are particularly widely used or renowned for their use in machine vision. So they're great at recognizing spatial patterns in multiple dimensions. And they've actually, though, despite their genesis in machine vision, hugely widely used in natural language processing as well.
Yeah, and it's the idea that if you want the local meaning of a picture, let's say I see in the background of your video, I see a guitar. Now, the guitar would be the same guitar if I moved it up or down or left or right or made it a little smaller, a little bigger. Convnets, in a way, are tricks that we use that allows us to use few parameters to solve those kinds of tasks. And that need for fewer parameters is always there. It makes the training of these systems much, much more efficient. And that is why it's so useful for data science applications.
Nice. And then the recurrent neural networks that you mentioned, those are traditionally associated with natural language processing. So they are adept at identifying patterns in a sequence. And so this could be a sequence of sounds, like the sound of my voice, or it could be a sequence of characters, a sequence of words. You could even use them potentially for financial time series or other kinds of quantities that vary over time. Yeah, and these are, I agree with you 100%. So I had seen Konrad's curriculum, and the way that they go about teaching the curriculum is very similar to the way that I teach my own deep learning programs and built my deep learning illustrated book. So I think it makes absolutely the most sense of I do kind of the same thing where the first part, the first third is focused on these foundational subjects, how you train a neural network, how the neurons make calculations. And then the second part is building on those foundations exactly like you are. And by coincidence, I suppose, I teach convolutional neural networks first and machine vision. And then second is recurrent neural networks. What then happens in week 3?
Yeah, and then in week 3, we talk about more advanced concepts that will include generative adversarial networks. I'm not sure if you've seen it. GANs, they're called GANs. They're super awesome. They can produce fake images of faces, for example. And we've probably all seen that. Like, is this image real.com or something like that? Where it draws images that you or me have real trouble distinguishing from reality. And so it makes these images, and we can do all kinds of graphics things with it. And it's a new set of techniques that are now starting to be really used in industry. Like think Photoshop.
Yeah, if listeners aren't familiar with generative adversarial networks already, GANs, which by the way is literally the next chapter that I do after recurrent neural networks. It's staggering how this is, it's convergent evolution somehow. And so you can go to...
Let me say something about convergent evolution. In reality, in the field, when it comes to teaching deep learning, we're all learning from one another. Here is John's book for people who see the video stream. So we are, of course, looking at all the other books, and we also called a lot of the other people teaching to figure out what's the best way of teaching things.
Incredible. That is a real honor to see that book there, Konrad. But so for listeners who haven't seen a generative adversarial network in action, a website that you can go to is whichfaceisreal.com, which Konrad alluded to. And I just looked up the URL here in real time to make sure that that was the right URL. And it's a fun way. It puts two faces side by side, and you have to guess which one is real. And yeah, generative adversarial networks, GANs, are getting extremely good at creating fake people. So interesting things. As you're saying, we kind of think about them in the context of deep fakes and the kinds of issues that come about related to these, but there's a huge opportunity in allowing this to augment human capabilities, where fashion design, apartment design, anything that happens in a visual space, all of a sudden you could be using these GANs to create beautiful photorealistic simulations of what you're trying to create.
There's another thing that's made by GANs, as far as I know. There is now an app on my phone where I can record a video of myself, just a short video snippet, and it can then make me sing to one of the popular songs. And it's really good at producing those videos.
Nice. Do you upload those to TikTok? Do you have your own TikTok account?
I don't have my own TikTok account, but I should be doing it. In particular, because some people at Neuromatch are now really interested in bringing what we are doing to TikTok, and I'm so curious to see how that will work.
Yeah, this is something we were talking about a little bit earlier. So something that regular listeners would know about is that I primarily use LinkedIn. A lot of our guests primarily use LinkedIn, and that's where we recommend connecting. But Konrad, with his academic background, one of the things that Konrad and I talked about first when we met was how he doesn't really do anything on LinkedIn that academics don't really. Meanwhile, on Twitter, he has over 20,000 followers. And when I make tweets, it's just like crickets. So it's funny how we end up with these different worlds. And now the Neuromatch Academy is making big strides in Instagram and TikTok. Is that right?
That's the plan, at least. Yes. I mean, I think in Twitter, for the academic community, Twitter fulfills a very important role, which is we switched from papers to preprints. Not like we are no longer waiting 2 years until someone publishes our papers.
Mm-hmm.
As soon as we wrote them, as soon as we submit them, we also put them on archive.
Mm-hmm.
So Twitter kind of helps me at least find the papers of other scientists, and that's why I think there's so many scientists on Twitter.
That's cool. It's amazing how things change. I mean, it's been 10 years since I was a serious academic, and I wasn't personally using Twitter as a means of getting papers, but I don't think it made as much sense because we weren't doing that real-time publishing back then in the same way.
Yeah, I think a lot has changed. But like, hey, let's briefly go back to the syllabus.
Totally. I was gonna bring us right back. So third week, we've got generative adversarial networks. What else? I bet you have deep reinforcement learning.
You bet. And not only do we have deep reinforcement learning, we will basically be doing deep reinforcement learning in the context of games. And you may have heard of AlphaZero, a set of algorithms that basically beat humans at like a whole host of computer games or non-computer games, like Go. No, like it's impressive to see. Go seemed impossible 5 years ago. Now beating a computer is impossible for all humans.
Right.
And that transition was brought in large parts by DeepMind, and Tim Lillicrap, who was part of those teams, will be teaching that. And it's going to be a wonderful day.
That's cool. Yeah, you really do have a lot of the big rock stars in the research field who are devising on the cutting edge of devising these algorithms, speaking as the lecturers on your curriculum. It is incredible. So you're talking about the board game Go there. So Go is, I think, the most popular board game in the world, but in the West, a lot of people don't know it. So you have there's a 2-player game, kind of like chess, and you have a player that has white stones, another player that has black stones, and you place them on a grid. And your objective is to encircle your opponent's stones. And when you encircle them, you capture them, and you get that territory on the board. And the computational complexity of this, I'm probably going to get this stat wrong, but it's something like the possible number of games, or the possible number of moves in the game of board configurations is more than there are atoms in the universe.
That's right.
Which is astronomically more complex than a game like chess, with which we had kind of expert system AI systems that could beat the world's best chess players like Garry Kasparov in the 90s. And so what made Go such a task so not only the computational complexity, but also there was this sense that the best Go players in the world had an intuition of how to be incredible, and that this intuition, a machine couldn't figure this out. And,
yeah.
And so I'm almost at my final point here, which is that if you don't know a lot about Go or deep reinforcement learning, a really fun movie that you can watch that has 100% rating on Rotten Tomatoes is the AlphaGo movie, which is available free on YouTube. It's also on Netflix, and it's about the story of machines becoming better than man at this, or people at this complex, supposedly intuitive game.
And I think it's a nice example why deep learning is so successful. Now, like if we look at how AlphaZero works or AlphaGo works, it combines two things. It combines a position evaluation. A position evaluation, basically, you look at the board and you're like, that's great, I want to play this, versus, this is a lost game. You have this position evaluation. You call it intuition, or humans might call it intuition. And you can then combine that with a piece that we understand very well, which is the planning into the future. Now, like as a function of how I put my stones, what's going to happen. And that allowed us for these games to combine our understanding of the game, which is in the rules. We can write it down as text or computer programs, together with like the intuition that implicitly is there in the neural network, which basically says, this is how games look like that are good, and this is how games look like that where you're really hopeless.
It's a beautiful thing. The things that are happening in the space are wild. This AlphaZero that you talked about. So AlphaGo was able to beat the world's best Go players at this one board game Go. And then AlphaZero, which you've mentioned a couple times, it's able to beat, it's a single algorithm that is even better than AlphaGo at Go, but also is better than any existing algorithm, and I think maybe even better than people at chess and a game called shogi, which is like a Japanese chess.
Yeah, the game of chess is no longer hard from a computer science perspective. Like,
Right.
it's fun to hear that because I remember when I started in the field, chess seemed so hard.
I just said it in such a silly way. Of course, if algorithms have been since the 90s been able to beat people at chess, then if an algorithm can beat any computer algorithm, it can obviously also beat all people. So that was a silly question for me to ask. Anyway.
Yeah, people are just not so good at playing games. Now, let me, in that context, plug the last day from the last week, which is
Yeah.
we'll then talk about the things where deep learning isn't good yet, the
Right.
things that we need to think about in the future. So, computer games, or like games like Go or chess, in a way they're easy because we know the entire world. Now, like everything that matters is right there on the board. But in practice, in the world in which we live that's around us, in which we humans live, most things are not known. Like I can't look into your head when talking with you. I can't. Like there's only a very small part of this complex world that we can actually see. And yet we somehow need to causally understand the world. Like how do aspects in the world influence other aspects in the world? And this problem of causality is something that so far deep learning has been very bad at.
Right.
And so we will basically spend a day talking about like the early approaches that people have to deal with these. And like the problems aren't just causality, there's also continual learning. For example, neural networks are really good in the way we usually use them at solving a task. But you're not solving a task, you solve a different task tomorrow. And the whole world will look differently. Like it's spring now. The visual world looks very different in winter. If you train neural networks on summer data only, you will be really bad at winter. And humans have preciously little problem with that. So this like how we can learn in a lifelong way is really interesting from a computational perspective, and we will round up the cost because we want our students to understand what deep learning can do for them, but we also want them to understand what deep learning cannot do for them. And that last day has an important role.
That is also the final chapter of my book, Deep Learning Illustrated. It's uncanny, except that I didn't have that continual learning piece in there. I hadn't thought about that at that time. But things like causality, and definitely where there's opportunities for big strides to still be made. And so here's an interesting, I mean, this is a bit of an open-ended question. So we've been talking about AlphaGo, we've been talking about AlphaZero. So part of what makes those deep reinforcement learning algorithms so interesting is that they're more and more general, and that they require less and less programming. So and less and less training data. So AlphaGo relative to AlphaZero, AlphaGo is amazing at Go. AlphaZero is good at many board games or many games with complete information. In the evolution of deep reinforcement learning algorithms, including AlphaGo precursors, we went from requiring lots of training data to requiring no training data at all and simply having the algorithm play against itself. And so this led to, this is a bit of a tangent, but it led to really interesting things happening because it meant that it didn't care what the standard curriculum was for learning how to play Go. It could learn advanced moves, or what we consider humans to be advanced moves. It could learn those early on and then learn some basic things later.
I also heard that it's gotten so good that now Go players will try and learn from how the algorithms play, because the algorithms don't have these human preconceptions that we are always bringing into it.
There was a quote from some champion Go player said that it's like watching aliens play the game. It's like this alien intelligence amongst us. So that's a bit of a tangent, but the point that I was trying to get to, and that I talked about in episodes 438 and 440, which aired earlier this year in January 2021, I talked about artificial general intelligence, and I talked about mu0, which is another algorithm, another artificial general intelligence, or another deep reinforcement learning algorithm that followed from AlphaZero. And so so artificial general intelligence. Let me take 1 second to explain what that is. It's this idea that you could have an algorithm that could learn as diverse a number of tasks as a person could. And so this ties into your point about continual learning and how learning is different. So, so is this an area that you work on in your research in particular? I guess if you're interested in intelligence in general, this must be a big part of what you think about and write about.
It's a lot of what I'm thinking about at the moment. I don't think we have great solutions yet, but
Mm-hmm.
I first want to point out how interlinked those things are. Like, if why do we want to understand causality? And a lot of people say, well, causality is kind of hard to define. What do we even mean with that? But in reality, we walk through this world. Most things in the world that we could possibly do are really bad ideas. Now, I can push the wall here at a random place. Nothing
Right,
will happen.
right,
But if I use the light switch, something will change. So
right.
there's a small, of all the things that we do, there's like a small number of channels with which we really influence the world, the future. At some level, if you give me only one task, I don't need causality. I just need to figure out what is my right move. But if you tell me, well, like quite possibly it will be dark later on, and you might want to figure out how to make the house bright, then I will try and figure out what those. I will have curiosity, and I will be interested in how causality works. So, at some level, these concepts like curiosity and causality, they drive from the fact that we are doing multitask, continual learning, that we are always preparing ourselves for what we will have to do in the future instead of just being good at one task. And that's in a way why even mu zero is easy relative to success in the real world. And animals can do much better behavior in the real world than any algorithm that we have.
Right.
Why? Because they've been pre-programmed to deal with this like continual lifelong multitask learning situations that we're in. And all animals that I've ever observed have like this deep desire to understand the world around them. And it's hard to give that to artificial systems.
Yeah. So, do you think that these kinds of approaches, deep learning, deep reinforcement learning, so we have these issues around causality, continual learning. Do you think that in time, these existing approaches like deep learning and deep reinforcement learning, that we can adapt them so that they are better suited to those problems, or do you think that we might need completely different approaches?
I think we can. I think that deep learning will always be part of how we'll solve problems. And in fact, a lot of people, including my friend Josh Vogelstein, say that we should never have called it deep learning. Because
Hmm.
what is it? What is it when we talk about deep learning? What is it really? It just means that we build system with lots of parameters. We figure out for each parameter, would it be better if we make it bigger, or would it be better if I made it smaller? And then we do it
Yeah.
on all of them at the same
Yeah.
time with like slightly clever approaches. But that arguably is just what we mean with learning. That's a system that makes itself better, and it's a system that is not low dimensional. So, in that sense, I think it has to be part of it, but I think we need to go beyond it. And I think as humans, we go beyond it. Like in our head, if I ask you, like, hey, John, like, want to come visit me in Philadelphia? You will run this program in your head. We're like, yeah, and then I go to Penn Station and I get on the train and I need to first buy the ticket. And you can do this reasoning there. And when it comes to these kinds of high level reasoning approaches, it's not enough to just build a neural network. Like, it's clear that we somehow need to deal with things that are a little like symbols. And I think this is a
Mm-hmm.
lot where the future of that field as we head towards general intelligence has to be.
Right. So yeah, you described, well, you kind of defined it, deep learning as gradient descent in a way where we're adjusting parameters, and so I might define deep learning as having these specific neural network algorithms and a few layers of them. But even, I guess even in deep reinforcement learning, we don't have multiple layers. Is it? Would you not define it that kind of way?
Yeah, so in a way, if I'm a little cynical, the word deep learning comes from artificial neural networks, how they were called before, being ridiculously uncool. So when I started entering the field and going to the NeurIPS conference, like late 90s, back then the number one predictor of your paper being rejected was it using the word neural network.
Even
So
at NeurIPS.
even at
Where-
NeurIPS, at that point of time, it should have been called KIPS for Kernel Information Processing System, because everything was about support vector machines.
Right.
So basically, when then it was clear from the work of Jan LeCun that there was a lot of mileage to be had, and like for a long while, he was having these digit readers that work quite well using artificial neural networks. But then when AlexNet came, which massively beat, so AlexNet was this network that the first one that people call deep learning, that basically just said, okay, let's use a really big algorithm, let's use graphics cards, let's use a whole bunch of other tricks to make things better, and then let's beat the guys at object recognition. And beat the guys at object recognition they did. So they beat the benchmarks by a massive amount, and they immediately replaced the previous machine learning approaches for object recognition. And so at that point of time, they needed a new moniker, because saying artificial neural networks would have made it sound bad. And some of the inventions helped them go deeper. Like AlexNet was deeper than previous. Why graphics card made that possible? Large data sets made it possible. And then a whole bunch of tricks. They use this thing which is called ReLU, which is almost linear. Like it's zero below some value, linear on the right-hand side. They used better ways of initializing the network. They used a cool way of using the hardware of the graphics card for the whole thing. So there were lots of innovations in that space that allowed the networks to be bigger, but like it's still an artificial neural network. Now it's like twice as deep, and by now it's 100 times as deep. But in a way, conceptually, I think it's the same intellectual line.
Nice. All right. So bringing it back a little bit, we were talking about whether deep learning approaches like this could be a part of having increasingly general algorithms, maybe an artificial general intelligence algorithm that has all of the capabilities of learning of a person. But you mentioned there that it would need to have a better representation of symbols. And so is that something outside of backpropagation, like some knowledge, some factual knowledge, like is of relationships that it gets from Wikipedia or something?
Yeah, I don't think it can easily be done directly in gradient descent. Now, like we can easily do things that you've never done before. Now, I can ask you, imagine a monkey jumps into Konrad's video frame right now and starts sitting on his shoulder. You can do that, no problem. We can't at the moment explain those things meaningfully to algorithms. Like how this thing, like add an object to a scene, is remarkably hard. And similarly, causal things. Like if I have a phone and I drop it, what's going to happen? You can very meaningfully say something to that. It's very hard to teach that to neural networks. And why? Because like at some level, things like phone, it's a symbol. Like you can say, sure, I can embed it in some vector space, but it still exists in the scene where I am. There exist so many objects. It's not that it's like just like a one big vector, and our representations of reality kind of support these modifications. Like add object, remove object. What would happen if? So there's a lot of things where it feels that the way we talk about things is actually more fundamental than a deep learning network would work with it. And if we look at the deep learning networks, these like semi-symbolic things are usually built into it. Like for example, AlphaZero. There is, or like AlphaGo. There is a very symbolic thing, which is like, how would the board would look like if I now use A7 and then I use B16 and then I use C3? If I play in that direction, that's kind of built in. But that is very symbolic if you think about it. That's very much not deep learning. And in the same way, if you look at more modern systems, you might have a recurrent system that does something and then does something else. It feels like in that sense, we're building in symbols into the architecture with which we interact with the neural network. So I think the future will see a lot of these systems that that have not just deep learning, but that also have a structure that matches the kinds of problems that you want to solve in the world in a symbolic way.
Very cool. That is such an interesting topic to hear about. Lots of food for thought for me, and I imagine for lots of our listeners as well. Konrad, how did you end up in this position where you are today, thinking about these problems? So, how did you become expert in both biological intelligence, biological neural networks, as well as artificial neural networks? What was your journey to becoming a full professor at the University of Pennsylvania, a distinguished university, studying this incredibly interesting thing? How did this happen?
Yeah, I think I just like to think about really exciting topics, and I always didn't feel comfortable doing the same thing for a long period of time. I feel like I will learn much more by exposing myself to many different disciplines. So originally I studied physics, but within about 2 years I decided that I find biology very interesting and started taking courses. And when the physicist in Heidelberg basically told me that that was a no-go for a physicist, I defected to Zurich.
Right.
And the guys in Zurich were like, sure, we consider brains to be a perfectly legitimate objective of study from physics. And then I went to London, learned a lot more about statistics. But I was already like, during my time in Zurich, I was building these little neural networks. I didn't think about it that it would eventually be a field, but I was trying to build neural networks to describe parts of the brain. And then I did some time in cognitive science, sometimes in statistics. And more broadly, I'm just interested in sitting down with exciting people and thinking about like the big problems in life and like the big problems for society. And and in that sense, my portfolio has been like this wildly overlapping set of projects, including molecular biology. We were working on this idea that we could use DNA as a ticker tape, as a like as a cassette recorder. No, what's DNA? It's
Whoa.
like a long tape.
Yeah.
Let's build a recorder that writes how and what a neuron does over time onto that tape. And so
Hmm.
we've been working on that. We've been working on a lot of different
Wow.
areas. And UPenn has this awesome professor position, which is called Penn Integrates Knowledge, whose official job description is bring the disciplines, bring the different departments at UPenn, the different schools kind of together and have projects that span those disciplines. And so for me, this is just like
Wow.
the most wonderful fit for what I've always been interested in.
It's PIK, Penn Integrates Knowledge.
That's right, yeah.
Cool. Wow. Yeah, that does sound like a really good fit for you. That sounds perfect.
But in general, I do believe that for everyone's careers, it's useful to expose yourself to different ways of thinking. So right now with the Neuromatch Academy, it helps me a lot about thinking about organizational structure that I would never have done before. I believe that for a lot of neuroscientists and cognitive scientists and material scientists and so on and so forth, getting exposure to deep learning is really important. Similarly, I believe for a lot of people who work as data scientists in a company at the moment, getting this set of deep learning ways of thinking about data science under their belt is going to be really useful for what they'll be doing in the future.
Yeah. And so I guess that's a way, something like the Neuromatch program that you've created. I mean, I mean, or that you're, is it fair to say that you created it, that you devised this? Or I guess it's something that came about with a number of,
It's a big group. I was with all the Neuromatch things. I was one of the co-founders of it, but it's a big group and it's too big a problem for any one person to pull off. Our CEO is Megan Peters, who's doing a wonderful job at managing of basically herding a lot of cats very effectively.
nice. And so where I was going with that is that it sounds like this curriculum that you've been involved in developing, it sounds like it's the perfect way for people to get to be able to apply these kinds of deep learning things in industry if that is something that they're interested in. You're probably deliberately tailoring it so that your own excitement, the excitement shared by people who are developing this curriculum, comes through in that whole program, and it allows people to go from uh, being data scientists without deep learning in their portfolio to being able to apply that in whatever industry they're in.
that's why we get together that amazing set of people. Like of course, someone like me could teach a deep learning course. In fact, at UPenn, together with Lyle Unger, I did teach the deep learning course. But we can make it much more meaningful by getting the world's experts together on that. But if we just get the world's experts on it, it would be ununderstandable. So we surround these experts with teams that give them really good feedback on what they can do, what people can realistically learn, and what they can't. What the things are that are really useful for people's careers, and which things they can learn in a more specialized course at a later.
Nice. So, other than deep learning, which it sounds like is clear from conversation with you that you think that it will continue to be a hugely valuable skill for data scientists to have for years to come, what other kinds of skills should our listeners be developing to prepare themselves for the future?
So I think, and this might just be my personal opinion, I think people need to think about causality. Why? What we really do as data scientists in the world is we help make things better. Now, we help companies make more money, we help companies be more efficient, we help people in science make better sense of their data, and so forth. What everyone really wants to do is make things better. What does it mean to make things better? It means that if we do A, things come out better than if we do B. This is fundamentally a causal question. And of course, we can A/B test, and everyone should know how to A/B test. Now we can like randomize things. Half of the people see one web page, half of the people see the other web page. We see which one has like the better click-through rate or something. But in many cases, we want to figure out how to make things better without being able to basically randomize everything.
Right.
There's a whole set of approaches for that. Quasi-experimental approaches is one that my lab is very interested these days. But importantly, everything that we tell someone, you should do X, you shouldn't do Y, is ultimately a causal statement. It says it will be better if you do this than if you do that. Machine learning doesn't answer those questions. It can be part of that, but we need to think in a causal way. We need to ask, okay, what would be better instead of what is correlated with it? Let me give you an example of how things can go badly wrong. Let's say we are in medicine. We take people that take some vitamin. We discover that the people who take that vitamin live longer than the people that don't have that. Now, should we recommend to everyone to take that vitamin?
Right. We don't have enough information. I don't know.
That's right. What could be going on? In that case, we actually know that people that are high socioeconomic status, have a lot of money, have time to dedicate for that, have money to buy the vitamin, are much more likely to take that vitamin. Now, also in American society, people that are rich tend to live longer than people that are not, which is a big problem. And now we're in that situation where in reality, the vitamin does absolutely nothing for your health. You could throw it out, no problem at all. But if we would just do simple-minded machine learning here, we'd find that there's a strong, significant correlation of taking vitamins with longevity. We would start recommending that to everyone. That would be wrong. And this kind of logic happens in every company, like on a daily basis. We want to be very careful about confounders, and that's something that in a way lives outside of traditional machine learning. I want people to think about causality.
Nice. That is a really thoughtful point to make. Nobody has ever answered that question on this podcast with that answer since I've been host, and it's a good one. It's so important and kind of obvious. So you sit, as we've mentioned many times, you sit at this very interesting position, straddling biological neural networks, artificial neural networks, what the meaning of intelligence is. So a question that I haven't asked a while on this show is, what do you think is going to happen in our lifetime? So let me frame that a little bit more. So you already talked about AlexNet, which in 2012, thanks to, as you alluded to, ever cheaper data storage, so much bigger data sets, much cheaper compute. The idea to do things on graphics cards instead of just regular CPUs. That has continued. So 2012 is now 9 years ago, and in that time, we have much, much, much cheaper data storage, much, much bigger data sets. Compute, same idea. We have these, huge parallel GPU systems and lots of open source software libraries like TensorFlow and PyTorch that take advantage of this highly parallel distributed GPU processing. So these trends will continue to happen for presumably decades. And we're also going to have ever more abundant sensors, 5G rollout, faster internet connections between everyone, sharing archive papers and conference proceedings and doing things like Neuromatch and learning from each other. And so we have more and more innovation and sharing. So technology in this space is advancing at a faster and faster pace every year. So what do you think is going to happen in our lifetimes? How interesting are things going to get?
Yeah, this is just a wonderful question. So I think you can make two very, very different stories. In one story, you're right. Like we keep pushing on deep learning of variants thereof. We kind of figure out these algorithms that ultimately can reason as good as humans. And we basically live in a hybrid world where half of the intelligent beings are robots, half are humans. And we pray that they don't overtake
Right.
and rule everything.
Right.
But you can make the exact opposite point. And I want to credit my friend Ben Recht as like having opened my eyes to that, which is every roughly 30 years or so, people discover regression. They discover all the wonderful things they can do with linear regression. And then at the end, someone points out that the real problems in life, like causality and actual real thinking, cannot be solved by it. Now, you can view modern deep learning as just one more of those examples. You can say maybe in the 60s we did regression in linear systems, and there was this huge excitement where people were like, hey, now you have a machine that can detect things. It will soon think like humans, and everything's going to be very different very soon. And then Marvin Minsky pointed out that there's like very, very simple logical problems that those machines can't solve, like the XOR problem. For listeners who don't know that, it's basically a system that has two inputs. They can be they're binary, 1, 0, 0, 1, and so forth. XOR means it should spit out 1 if it gets 1, 0 and 1, 1 as input, and otherwise it should spit out 0. And it's provably not solvable by a linear problem. And now you can say, like 30 years later, people are back, neural networks are back, and they do backpropagation. And everyone gets super excited about all the problems that they will solve. And pretty soon people point out that like a lot of the interesting problems cannot be solved by it.
Right.
And now you can say, we are just in this early phase. Now and a lot of things might feel like they're very cheaty. Now let's say GPT-3. GPT-3, for people who haven't heard about it, it's this wonderful natural language processing thing, and you will hear a lot about it if you go to a Neuromatch. You can prompt it with some text, and it generates text, and it feels almost like English. It definitely feels like English language. Now, if you first see it, you're super impressed about it. But GPT-3 has basically been trained on just about every text that has ever been said on the internet. So it has this massive training data. Now, it just turns out that under most circumstances, people say the same sentences over and over. But a human can meaningfully reason with you based on a very small data set, and GPT-3 consumes all the data in the world, and it makes the most elemental logical mistakes. For example, if you give it the prompt, tell me the story of here's a couple of unicorns that live on a mountain, they speak English. And the first sentence produced by GPT-3 is, in this space, there's the unicorns, they have 2 horns each. And you're like, hold on, what? Yes. We talk about unicorns, and you talk about 2 horns each. And it turns out that like 1 horn, 2 horn, it's all correlated in big data sets.
Yeah.
But you see what that problem is.
Yeah.
There's just
Exactly.
there's no real understanding. And so in that sense, you can say, sure, we will use deep learning to solve all kinds of business relevant problems and like academic problems, but it will always just be a part of it. And the really interesting things, like how we figure out how the world really works, in a way happen outside of that space. Now, where on that continuum we are, I don't know. No, like there's gonna be like a little bit of like we really move things forward. We might have self-driving cars or something like that, but there will also certain problems that it's not really very good at solving.
Beautifully said. That was, yeah, beautifully said. I definitely fall into disillusion a lot about this time being different, you know? And you're right, though. We're still, whether we have the regression model happening over many neural network layers, it's
Yeah.
still a regression model. But what about
And
quantum computing? Isn't quantum computing going to, or using DNA? We'll have DNA computing. Everything will be different, and it'll be causal because it's DNA or quantum. That's what we need. It needs to be DNA, quantum computing, and then we'll figure out the causality. It'll be a pinch.
in fact, let me give you like a great example of kind of misinterpretation, a great other example. So neural networks usually have this property that you can do adversarial attacks on it. What does that mean?
Mhm.
I can show you a picture of a banana and put a sticker on top of it, and your neural network will say, this is a toaster. It's just that that sticker that I put on basically contains features that very much look like a toaster. In
Right.
reality, a banana with that property never happens. But if you'd see that thing, you'd be like, that's a banana with like a weird sticker on it. But a neural
Right.
network will be, that's a toaster. Now,
Right.
it actually works quite well in the real world. If I take an object and I attach a sticker to it, which has written in English text the name of something else, it's often wrongly recognized as the thing that I write on it.
Mm.
So what that means, if I take a car, I put a sticker on it which says empty trash bag. A lot of algorithms will think this is an empty trash bag.
Right.
And I think I can't get that idea out of my head to go once, like, like self-driving Teslas all over the place, to walk through the city with a friend and basically stick a little, this is an empty trash bag, to all the parked, like really expensive cars.
Right.
And then observe how like a bunch of Teslas destroy the entire city.
Right.
Why? Because because
Did you make up that one? Did you make that one up on the spot, or have you come up with that one before? That was really good.
I thought about it like a
That's
little bit.
great. I love that.
But what it means is that there is this adversarial attack on neural networks that humans wouldn't have. That is truly pragmatic, like, and you can't guarantee that a neural network will not encounter an adversarial environment.
Cool. Well, I'm sure we could talk about this for days and days and days. And maybe we'll have to have you on another episode soon to get even deeper into some of these topics. But we should start winding down the episode, which means that it's time for that staple question at the end of the Super Data Science episode. Konrad, do you have any book recommendations for us? Maybe about things we've been talking about today, or just, I'm sure whatever is interesting you, whatever you've been reading about will be great.
Yeah, so I can highly recommend to anyone listening to this to read a book on causality, because as you heard, I think that understanding the world causally is very important. The most accessible introduction to that, probably at the moment, is The Book of Why by Julia Pearl.
Uh-huh.
The Book of Why is a beautiful, readable exposition of the need to think about the world around us in causal terms.
Nice. I almost shouted out Judea Pearl, rudely interrupting you, but when I did that, I was thinking it was going to be his causality book. And of course, Book of Why is an even better recommendation because I think it's way more accessible. I wouldn't go around recommending Causality by Judea Pearl to my friends.
Yeah, Causality by Julia Pearl is a wonderful, deep, thoughtful book for specialists who want to specialize in causality.
Right.
The tools that Julia Pearl exposes allow you to prove exactly under which circumstances you can know or not know about causality. It's just a wonderful set of ideas. But the Book of Why makes it live for people who haven't been in the causality space for a long time.
Nice. That is a great recommendation. And then I have a recommendation, which is that if you're looking to get into deep learning and you're able to take 3 weeks off, take this Neuromatch curriculum that Konrad is helping set up. I am so jealous of anybody who gets to learn deep learning that way. I wish I could go back in time and have that be how I did it. It sounds like an absolutely perfect curriculum.
And I wish I could go back in time for that.
Well, these kids these days are so lucky. And also I'll note that, so one of the prerequisites that you mentioned, so you mentioned things like, linear algebra, being able to do simple matrix operations and being able to calculate derivatives. So between now and August, if that's what's holding you back from signing up for Neuromatch, I've created a machine learning foundations curriculum, which teaches exactly those topics, linear algebra and calculus, and in the context of machine learning, and also using Python libraries like NumPy, TensorFlow, and PyTorch. So this would be probably something that you could do in the interim and be all set to take the Neuromatch program by August. So I think that is very exciting. How should our listeners contact you? My guess, your number one pick would be Twitter, and then number 2 is TikTok.
No, I think number one is definitely Twitter, but you can reach me on LinkedIn. There's far fewer people competing for their messages being seen by me on LinkedIn.
Yeah, after talking with me a couple months ago about LinkedIn versus Twitter, Konrad is now giving LinkedIn a shot and he's making posts. So if you want to get his attention, he has only 1/10 as many followers on LinkedIn as on Twitter. So you can go bother him on Twitter. You can like and love his posts, and he'll really appreciate it because he feels like there's too many tumbleweeds.
Yeah, LinkedIn, if you come from the outside, is just like a bizarre environment.
Yeah, I won't disagree with you on that. All right, so thank you so much, Konrad, for being on the show. I learned so much. I had so much fun, and I hope to have you on again sometime soon.
Thanks for having me.
What a terrifically interesting episode. Thanks to Professor Körding, we were able to dig into the innovative Neuromatch curriculum that enables small groups of students with similar interests to learn deep learning together. Convolutional neural networks, recurrent neural networks, GANs, deep reinforcement learning, we covered all of the major approaches in deep learning, including the revolutionary AlphaGo and AlphaZero models. We also covered where deep learning doesn't work today for enabling human-level intelligence in machines, such as issues with causal inference and continual learning. The understanding of symbols was a potential solution that Konrad brought up to overcome these issues. Wonderful to be able to learn from a deep AI expert like Konrad. As always, you can get all the show notes, including the transcript for this episode, the video recording, any materials mentioned on the show, and the URLs for Konrad's Twitter and LinkedIn profile, as well as my own. LinkedIn and Twitter details at superdatascience.com/469. That's superdatascience.com/469. I'm always happy to meet listeners, so please do connect and feel free to tag me in posts with your thoughts on the episode. Your feedback is invaluable for figuring out what topics we should cover on the show next. Since this podcast is free, if you'd like a hugely helpful way to show your support for my work, then I'd be very grateful indeed if you made your way to the Data Community Content Creator Awards nomination form. The link is in the show notes. Obviously, we'd hope you could nominate the Super Data Science podcast for Category 7, the podcast or talk show category. I'd also love my name, John Crone, nominated for Category 8, the textbook category for my book Deep Learning Illustrated. And finally, I'd also love my name, again, John Crone, nominated for Category 2, the Machine Learning and AI YouTube category for my YouTube channel, which contains tons of free videos on deep learning, linear algebra applications, and machine learning libraries. The Data Community Content Creator Awards themselves are coming up on June 22nd, and I hope to see you there. All right, thanks to Ivana, Jaime, Mario, and JP on the Super Data Science team for managing and producing another incredible episode today. Keep on rocking it out there, folks, and I'm looking forward to enjoying another round of the Super Data Science podcast with you very soon.